Dear students, in the previous lecture we have discussed about the types of the electric heating, and after this we have discussed the power frequency heating, which includes the resisting heating, and after this further its type: direct resistance heating and indirect resistance heating, along with its construction, working, and applications has been discussed. Today we are going to discuss about the induction heating. The induction heating works on the principle of transformer, because in transformer we know that the energy is transferred from the primary side to the secondary side on the phenomena of electromagnetic induction. And also we know that in transformer there are certain types of losses in it. One of them are the core losses and one of them are the copper losses. Core losses are further divided into two parts. One is the hysteresis loss and other one is the eddy current losses. In induction heating, we normally consider the eddy current heating. The induction heating is also known as eddy current heating. The currents are induced by the principle of electromagnetic induction. The induction heating may be low frequency, as in case of core type induction furnace, or high frequency, as the case with coreless induction furnace. On the basis of the frequency, we can divide the induction furnaces into two types. One is the core type and the other one is the coreless type. The types of induction heating are direct induction heating and the indirect induction heating, just like the resistance heating which we discussed in the previous lecture. Now, what is the direct induction heating? In direct induction heating, the eddy currents are produced within the material itself that is to be heated. So here what we are going to do, that the eddy currents are produced within the material which we are going to melt or which we are going to heat. The example of direct induction heating are the high frequency eddy current heating used for case hardening or tempering of various machine parts, annealing of steel strip, and soldering. The core type induction furnace used for melting non-ferrous metals such as copper, zinc, and brass. Coreless induction furnace used for preparing various high-grade steels also work on the same principle. So, if I am going to conclude the direct induction heating, I can say that the direct induction heating is that heating where the material act as the secondary and the eddy current are produced within that material which is to be heated or melted. So direct induction heating occurs in both type of induction furnaces, the core type induction furnace as well as on the core less induction furnaces as per the requirement. Now what is the indirect induction heating? The example of indirect induction heating is the indirect induction oven, which is in direct competition with the resistance oven and is preferred over it due to its fine temperature control. It is used for the same purpose as the resistance oven. So in this paragraph, we have just made the comparison of the indirect induction heating with the resistance heating, with the indirect resistance heating, and Why we are going to prefer the indirect induction heating in comparison to the indirect resistance heating? Moreover, in the indirect induction heating method, the eddy current are induced in the heating element by electromagnetic induction, which produces heat in the heating element. Here, the eddy currents are not moving within the material, as in case of direct induction heating. Here, the eddy current are induced in the heating element by electromagnetic induction, which ultimately produces the heat in heating element. The heat thus produced is transferred to the body to be heated by radiation phenomena. In direct induction heating, the eddy current are circulating within the material. However, in indirect induction heating, the eddy current are induced in the heating element by electromagnetic induction. So, as we have discussed just before, there are two types of induction furnaces. One is the core type induction furnace, and the other one is the core less induction furnace. One by one, we will discuss in detail the construction and working and applications of the core type induction furnace and the core less induction furnace. Now, what is the principle of core type and core less induction furnace? So first we will go for the principle of core type induction furnace. In the figure, core type induction furnace is shown. Core type furnace is essentially a transformer with the charge of metal to be heated as a single turn short circuited secondary and magnetically coupled to the primary winding by iron core. In the figure, we can see easily that this one is the magnetic core, this one is the primary winding, which is connected to the supply, and this is basically a single turn short circuited secondary wherein the charge is placed within the crucible. Basically, the crucible is basically the material or beaker or any material which contain the charge. The current flowing through the charge is very high, maybe of the order of several thousand amperes. So you can imagine how much is the heat is going to produce, because we know that I square R is the loss or the heat. From the figure, it is clear that the coupling is loose and leakage reactance is high, hence the power factor is low. So the first limitation of the core type furnace is that its power factor is low. So to overcome this issue, this furnace is operated at a very low frequency, say 10 Hertz. The second disadvantage is that electromagnetic forces produces great turbulence of the molten metal, which is useful to a certain point, but it becomes too severe unless frequency is kept low. So the second issue with this is that a great amount of turbulence occur when the charge within the crucible melt down. Another disadvantage of this furnace is that a crucible is of inconvenient shape from metallurgical point of view is used. This is the constructional defect. At the time of starting, a complete ring of metal must be present in the crucible, otherwise the secondary circuit will remain open and heat will not produce. Whenever we are going to start the furnace, we are going to melt any material, then it is better to put some metal ring within the crucible so that secondary becomes short circuited and huge amount of current can easily flow within it. Yet another disadvantage is that it requires low frequency supply, which can be had by using motor generator set or frequency changer, which involves extra cost. Since we are working on the low frequency, so definitely we have to lowers the frequency from the nominal value by using any mean. On account of above drawbacks, such furnaces have been obsolete nowadays. So what type of core type furnace is used normally? That one is the Ajax wet furnace or vertical core furnace. An improved form of core type furnace is Ajax wet vertical core type furnace, which is explained below. This furnace is very suitable for continuous operation, and it can be operated on normal supply frequency, that is 50 Hz. So the first drawback, so the two drawbacks has been covered up. One is it is simple operation and there is no change to put extra equipment to regulate the frequency, to minimize the frequency, to decrease the frequency from the nominal value to the 10 Hz on any other range. This type of advanced form of induction furnace is operating at 50 Hz. The core is made of laminated steel and the secondary circuit is formed by a single ton of molten metal. There is a laminated steel within the core in order to avoid saturation at high frequencies. And the secondary circuit is of single ton of molten metal. The charge is given from above and molten metal is taken out through the spout at the bottom of the furnace. We put the charge from the upper part and we take the molten metal from the bottom. The steering action is produced by the pinch effect, which is proportional to the square of ampere turns. So it means that in this scenario, automatic steering action is going to take place based on the phenomena of pinch effect. The secondary circuit is only complete when there is sufficient molten metal in the V to complete the secondary circuit. So here this V basically representing the bottom part of the vertical core furnace. So before I go ahead, I will show you the picture of this type of furnace. So the V shape is here. You can see easily that it is the bottom part of the furnace. Okay. Here in the upper part, there are 5 bricks. This one is the bricks. We put the charge from here. This one, and this one are all the cores. This one is the primary winding. This one is the V-shaped secondary channel. This one is basically the spout from where we can get the molten metal. So this is basically the shape of the vertical core type induction furnace. In case the furnace is to be kept overnight without operation, a reduced voltage is applied which supplies just enough energy to keep the metal in V in molten condition. Because if the temperature becomes less, the metal becomes hard. It will not be soft. And when it becomes hard, it is very difficult and quite impossible to empty the crucible, which is V-shaped in condition. The furnace therefore is very suitable for continuous operation. A proper arrangement is made for fitting the furnace to take out molten metal. The power factor of the circuit is about zero point 0.8. In simple core type induction furnace, the power factor is low because of the reactances and other loose connections, and the power required for furnace in order to complete melt in a reasonable time is about 200 kW per time. The melt is completed in about 1.5 to 2 hours for large sizes and in lesser time for smaller sizes. Now, what are the uses? The furnace is used for melting and refining of non-ferrous metal like brass, copper, and zinc. Its efficiency is about 75%. Standard sizes of these furnaces are 60 to 300 kW, single phase 50 Hz working at 600 volts. Now, what are the advantages? Advantages includes are that its control is very simple, ideal working condition in cool temperature with no dirt, noise, or smoke, high power factor 0.8 to 0.85 comparatively. Fourth one is the absence of crucible, and the fifth one is the uniform steering of charge gives homogeneous composition. Now we will move towards an example. Estimate the energy required to melt 0.5 ton of brass in a single phase induction furnace. Now what we have to find? We have to calculate the energy required. For what purpose we required energy? To melt 0.5 ton of brass. If the melt is to be carried out in half hours, now he has given us the time here, what must be the average power input to the furnace? So if we melt the 0.5 ton of brass for half an hour, how much is the energy, how much is the power required by the furnace? After this, he has given some of the specifications related to the brass, that the specific heat of brass is 0.094, latent heat of fusion of brass is 39 kilo cal per kg, melting point of brass is 920 degrees Celsius, furnace efficiency is 60.2, and the temperature of cold charge may be taken as 20 degrees Celsius. So when we are going to input the brass within the furnace, its temperature is 20 degrees Celsius, and when it going to become melt, it going to become melt at 920 degrees Celsius. So we required the amount of energy to melt the brass. So the quantity of brass to be melted is 50 kg. 0.5 tons means that it is 500 kg. Sorry, it's 500 kg, not 50. It's 500 kg. Heat required to raise the temperature of brass from 20 degrees Celsius to 920 degrees Celsius is H1 is equal to mass multiplied by the specific heat of brass multiplied by the rise in temperature. So we have to calculate we know that the initial temperature is 20 degrees Celsius and the final temperature is 920 degrees Celsius. So how much is the rise? 920 minus 20, so 900 degrees Celsius temperature rise. We put the values. Mass of the brass is 500 kg, specific heat is 0.094, and the rise in temperature is 920 minus 20, which is equal to 42300 kilo cals, kcals. Heat required to heat the metal at 920 degree, because we have already discussed in the theory that we have to kept the temperature constant so that the charge or the metal will be in the molten state. So here we say that H2 is equal to M multiplied by the latent heat of fusion of brass, L. So here H2 is equal to M multiplied by L. M is the 500 multiplied by 39 is the latent heat of fusion of brass, which is 39 kilocal per kg. So the heat to require the charge to be in molten state is 19500. So how much is the total heat required is the H1 plus H2. H1 heat is required to keep the charge, to change the state of the charge from the solid state to the molten state. And H2 is the amount of heat required to keep it in the molten state. So H is equal to H1 plus H2, which is equal to 42300 plus 19500, which is equal to 61800 K. So as per requirement, how much is the energy required in all this process? So the formula is that the energy required is equal to heat required multiplied by 4180. So 4180 is 1 kcal is equal to 4180 joule. 3600 is basically representing the time in 1 hour, which is equal to 60 minutes multiplied by 60 seconds. So we get the 3600 multiplied by 1000 mean that we want to get the value in kWh multiplied by the furnace efficiency. So heat required we have calculated 61800 kcal. 1 kcal is equal to 4180 divided by 3600 multiplied by 1000 multiplied by furnace efficiency, which is equal to 60.2%. So 0.602. We just solve this value, we get the value of 119.5 kWh. So energy required to melt 0.5 ton of brass in a single phase induction furnace is 119.5 kWh. So all this is about the core type induction furnace. Now we will move towards the core less induction furnace. No core is provided in the core less induction furnace, as the name indicates that there is no core in this type of furnace. A crucible of more convenient shape can be employed. In this case, also the charge to be melted is made the secondary of the transformer. The primary is wound over the crucible itself. The eddy current produced in the charge not only heat it up, but also account for the stirring action. In the figure, there is no core, but there is a crucible which is shown by this. These small circles are basically the primary winding, which is connected with the crucible. And within the crucible, there is the charge or the material which is to be heated or which is to be melted. Iron laminations are provided outside the primary winding to create a low reluctance path for flux, and also contain the stray field which may otherwise induce heavy current in the supporting steel structure. The frequency employed depends upon the size of the furnace. For lower capacities of furnaces, higher frequency of the order of 3000 Hz are employed, whereas for higher capacities, frequencies are down to 600 Hz. If the capacity of the furnace is small, then the frequency range is high. If the size of the furnace is small, is large, then the frequency goes down. To reduce copper losses, hollow copper tubes are used in which cold water is circulated. So this cold water is just to uh, minimize the copper losses, minimize the heat due to copper losses. The furnace is chiefly used for melting of steel and other ferrous metals. The capacities available vary from 50 kg to about 20 tons. The initial cost is more as compared to arc furnace. Now, what are the advantages of the coreless induction furnaces are that it has low operating cost, it has automatic steering action produced by eddy currents, it has low erection loss, absence of dirt, smoke and noise, it has less melting time, it has simple charging and pouring, precise control of power, and more suitable for production of high grade alloy steels. Now we will go towards the method of obtaining of power supply for coreless induction furnaces. For coreless induction furnaces, power supply is obtained from ordinary supply system and its frequency is converted to higher value by means of oscillators. The oscillators can generate very high frequency of the order of megahertz. So here we have to as an oscillator is provided with the coreless induction furnace to regulate the frequency. The AC supply is stepped up by the transformer and then rectified by using bridge rectifier circuit. The rectified voltage is supplied to the oscillator and high frequency output is fed to the charge to be heated through the output transformer. So for today it is enough. In today's lecture we have discussed about the induction heating, the types of induction heating which includes the direct and indirect induction heating. After this we have discussed about the types of the induction furnaces, the core type and the coreless type induction furnaces, and their construction, working, use and advantages. Try to study all this, and if you feel any confusion or if you have any question, do ask me during the lecture hours. So today it is enough, and thank you very much for giving me time. Allah Hafiz.